Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue thinking about deformation and metamorphic rocks. So in this video we're going to be thinking about how does metamorphism occur, and this is going to correspond to section 8.8 of your textbook. So on the slide here you can see we have a diagram that's showing us four of the ways through which metamorphic rocks can be produced. Now we already know that pressure and temperature are going to be the major causes of the formation of most metamorphic rocks, because it's the changes in pressure and temperature which drive the mineralogical changes which are a part of metamorphism. So a lot of metamorphism simply is due to changes in mineralogy. Now, there are other ways in which we can induce metamorphism though. So tectonic stress is also going to be a cause of metamorphism. So if you remember the metamorphic rock slate, you will remember that it is a metamorphic rock that consists of clay minerals that have been compressed and forced to align themselves, producing a slaty cleavage. Now, with regard to the mineral makeup of that rock, it's actually pretty much identical to the clay-rich sedimentary rock from which it formed. The clay-rich sedimentary rock contains clay minerals, and so does the slate. So, from a mineralogical point of view, they're pretty much the same. The only difference is the presence of the metamorphic fabric, the slaty cleavage, which has been produced by compression. So even though there's been no change in the mineralogy, the application of a tectonic stress has forced the minerals to align, leading to the formation of a new metamorphic rock. The other way in which we can induce metamorphism is through the presence of fluids. These are typically hydrothermal fluids, so hot waters. Now, what will happen is as these hydrothermal fluids circulate through the Earth's crust, they will scavenge elements as they go. So they might steal some calcium from one mineral, some iron from another mineral, maybe some sodium from another mineral. And eventually what's going to happen is this hydrothermal mineral is going to come across a layer of rock with which it can react. And there will be a chemical reaction between the minerals in the rock and the water and the material which is dissolved within that water, and that's going to lead to a chemical reaction, and this chemical reaction is going to lead to the original minerals breaking down and their replacement by new minerals. So this is also considered to be a type of metamorphism. Now, in terms of metamorphism itself, it's broadly split into two categories. The first type of metamorphism is referred to as contact metamorphism, and this is associated with bodies of magma which are moving through the Earth's crust. So in this model you can see we have a sequence of sedimentary rocks, and into this sequence of sedimentary rocks we have a magma intruding. Now, what's happening is our magma here is going to be very, very hot. It's going to be hundreds of Celsius, anywhere between about 750 Celsius all the way up to somewhere in the region of 1300, 1400 Celsius. And so this very, very hot magma is obviously going to start heating up the rock with which it is in contact. So obviously heating up the rock is going to increase the temperature, and this is going to drive metamorphism. So this increasing temperature is going to cause the minerals along the edge of the intrusion to become unstable, and so the minerals in the rocks are going to start changing into new minerals which are stable at the elevated temperatures. Now, the most important thing to remember about contact metamorphism is that it can only occur in areas where there is a temperature difference between the magma and the crust. So obviously if we have a magma that's at 750 Celsius and the rocks with which it is in contact are also at 750 Celsius, there is not going to be any metamorphism taking place. So we need to have a temperature difference. Now, normally this kind of temperature difference can only really be established in the upper crust. Typically the lower crust is very often just too warm, so not much contact metamorphism occurs down there. So this means that contact metamorphism is often associated with high temperatures because of the magma, but the pressure is often considered to be quite low because this type of metamorphism only takes place in the upper portions of the Earth's crust. Now, the other type of metamorphism which we can perform, well, which forms metamorphic rocks, is regional metamorphism. Now, regional metamorphism is a process through which we create large volumes of metamorphic rock. And regional metamorphism is most commonly associated with orogenic events, mountain building events. And of course, we know that these are most commonly associated with convergent plate boundaries. So regional metamorphism is often associated with convergence, and this can of course be ocean-continent convergence or ocean-ocean convergence. We don't tend to get a lot of I do apologize, that should be ocean-continent or continent-continent convergence. We don't tend to get a lot of regional metamorphism when we're dealing with ocean-ocean convergence. So regional metamorphism is typically the result of both increasing pressure and temperature. And the reason for this is as part of the convergent tectonic event, we end up forming a mountain range, and this causes the crust to become noticeably thicker. Now, this thickening of the crust means that the rocks at the towards the base of our crust are obviously going to be exposed to increases in pressure and temperature, and this is going to help to drive the regional metamorphic process. So what are the three causes of regional metamorphism? Well, the first cause is quite simply burial. So in regional metamorphism, it's not uncommon for rocks to be compressed, causing them to become thicker, or for pieces of rock to be thrust over the top of pre-existing sequences. Remember, this is due to compressive plate tectonics. And so what will happen is, as material gets deposited on top, the rocks down here at the base of our sequence are going to steadily be exposed to higher pressures and temperatures, and the deeper they get buried, the higher those pressures and temperatures will become. And so this means the rocks which find themselves in the core of our mountain range are going to find themselves being exposed to very, very high pressures and temperatures, and so they're obviously going to metamorphose. Now, as we get to higher levels, so as we move towards the surface, the degree of metamorphism is going to steadily decrease because obviously the pressure and temperature are dropping. We are also going to get metamorphism associated with the process of subduction. So in the process of subduction, we have ourselves a piece of oceanic crust which is subducting under a piece of, in this case, continental crust. Now, what happens here is we have a situation where we have two bits of rock smashing into each other, and this is obviously going to lead to very, very high pressure. At the same time, though, what we have is a situation where we have lots and lots of water circulating around, and this water is going to be able to pick up the heat created by the convergence, and it's going to transport it away from the area, so it's going to take it away. Now, this means that at the subduction zone, what we have is a situation where we have very, very high pressure, but surprisingly low temperatures because the water is constantly taking away the heat. And so this is going to lead to a very specific type of metamorphism, which is often referred to as subduction metamorphism, and it's often defined as having high pressures and low temperatures. The final type of metamorphism which will often occur during a regional metamorphic event is metamorphism associated with hydrothermal fluids. And this is quite simply because the thickening of the crust during the mountain range's creation will lead to the rocks at the bottom of that sequence getting deeper and hotter. And so if there's any fluid in these rocks, that fluid will also become hotter, and so that will naturally encourage the fluid to become more buoyant, and it's going to want to rise up. And so the fluid is going to start circulating. As fluid gets heated up, it's going to rise. That fluid is going to cool down, and then it's going to sink back down. So we're going to end up with convection of our fluid in the crust. And so obviously the movement of this fluid can lead to reactions between the rocks and the fluids, and this is going to lead to metamorphism. So what chemical processes can actually occur during metamorphism? Well, the first chemical process that can occur is recrystallization, and we've already touched on this. So recrystallization is when we take an existing mineral and we turn it into a new mineral that has the same composition. So the example we've used is the transition of aragonite to calcite when temperature increases. So in both cases, aragonite and calcite, the chemical formula is the same. It's CaCO3, so calcium carbonate. However, aragonite is most stable at lower temperatures, whilst calcite is stable at higher temperatures. So as we begin to expose our rock to increasing temperatures, any aragonite that's present will become unstable and it will recrystallize to give us calcite. Now, we can also have the other process, which is of course alteration, which is when we have an existing mineral changing into a new mineral that has a completely different composition. So just bear that in mind. Recrystallization and alteration are actually slightly different processes. In recrystallization, the chemical composition of your mineral remains stable. In alteration, the chemical composition of your mineral will change. Now, during the recrystallization or alteration event, we will obviously end up producing new minerals. And if these minerals are platy, so like a piece of paper, or if they are elongate, like a pencil, then as they develop and grow, they will preferentially align themselves at 90 degrees to the direction in which the rock is being compressed. And so this will lead to the formation of a foliation or a lineation. So obviously, if we are going to form a foliation or a lineation, we need compressive tectonics. And so this means that rocks which tend to have foliations and lineations are very often associated with regional metamorphism, which is associated, of course, with the convergence of tectonic plates. So that convergence causes the compression that leads to the formation of foliations and lineations. In contrast, when we have recrystallization in lower pressure environments, so let's say contact metamorphism, there is no tectonic stress which is going to force the minerals to align because the pressure is relatively low. And so this means that rocks which tend to be associated with contact metamorphism will very often not have foliations because there's nothing making those minerals align. They simply grow in whatever orientation they like. So another chemical process which we can see occurring with metamorphic rocks is the process of pressure solution. So in the case of pressure solution, what we have is we have crystals of a mineral which is relatively robust, and the classic example would be quartz. Quartz is a surprisingly tough mineral. It's very difficult to make quartz do anything with regard to metamorphism. It just doesn't really do much because it's so chemically inert. Now, what can happen though is you can see we have several quartz crystals here, and you can see these quartz crystals are in contact with each other. Now, what we're going to do is we're going to put our rock containing these quartz crystals under increased pressure. And so as we put these crystals under increased pressure, what's going to happen is the point where these crystals are in contact with each other is actually going to start to dissolve and melt because the pressure is focused on this point right here. And this very, very highly concentrated region of pressure is going to cause the crystals to begin to break down at the point of contact. And slowly over time, what's going to happen is it's going to allow these crystals to begin to fuse into one another because of this pressure solution. Now, the quartz which is liberated through this process at the point of contact is going to flow away, and typically what will happen is it will fill in voids in the rock, or it can leave the rock completely and go somewhere else. And so this is the kind of process that we find occurring when we have sandstones being turned into quartzites. So in our sandstone we have lots and lots of quartz-rich clasts, but these quartz-rich clasts aren't actually going to be that metamorphically active. They're just going to sit there. However, as our sandstone gets exposed to steadily higher temperatures, these quartz crystals are going to start to be pushed into one another, and they're going to start fusing together due to pressure solution. And so this is going to be the process that takes our sandstone and turns it into a quartzite. The final chemical process which you'll often encounter during metamorphism is remobilization. Now, I'm going to be honest, this is actually a bit of a tricky process, and geologists are still a little uncertain about the exact mechanisms involved in this process. So just bear that in mind. So, remobilization is a bit tricky. So in the case of remobilization, what happens is we see certain minerals will preferentially begin to appear in certain bands. And of course you might think, right, this relates to gneisses, and yes it does. So remobilization is the reason which we get these light and dark bands which we see in certain metamorphic rocks, especially gneiss. So the thing you're wondering is, okay, well, how are we taking these dark coloured minerals which are normally randomly distributed throughout our volume of rock, and how are we forcing them to form a distinct layer? And this is actually the process that's a little bit difficult to explain. And so we think there's actually a range of possible ways in which this could be happening. So we think that the first option is that our minerals could simply be diffusing. So our minerals diffuse from their current locations and they reprecipitate themselves to form a distinctive band. Another possibility is that these minerals are being dissolved in a fluid, so something like water. So these dark minerals dissolve into the water moves through the rock, and it reprecipitates the dark minerals once again, forming a band like so. The other possibility is that these minerals actually partially melt, so they begin to form a small volume of magma, and this magma begins to move through the rock, and once again the magma then crystallizes, producing a band of dark minerals. So it doesn't really, the mechanism is actually a bit difficult to explain, but whatever actually causes the effect, we end up with bands of light and dark minerals forming in our rock. And these bands of light and dark minerals will very often form at 90 degrees to the direction in which our rock is being compressed. And so it's quite likely that the growth of these crystals, or the regrowth of these crystals should I say, is being controlled to some degree by the pressure being put on the rock, forcing these minerals to grow parallel to each other, producing an alignment. We can also have physical processes taking place during metamorphism, and so these are primarily going to be due to increasing pressure and shearing. So we've already seen several examples of conglomerates which have been metamorphosed. And so in these types of rocks where we have large clasts or where we have large crystals, the process of putting the rock under increased pressure can sometimes lead to these clasts or crystals becoming flattened due to nothing but the pressure. And so this will lead to the deformation of objects, and they'll take on a more flatter, more pancake-like appearance. And so we can use that to say, right, this rock has obviously undergone quite an extreme compressive stress. And obviously when we squish our rock, so in this case we're squishing our rock from left to right, we will end up causing our minerals, crystals or clasts to deform and orientate themselves approximately north-south, because once again the compressive force is going to cause them to deform at 90 degrees to the direction in which the rock is being compressed. Now, this is arguably one of the most common processes that can occur in metamorphism, and this is rotation. So rotation is the process which occurs when we take a muddy sedimentary rock and we turn it into a slate. Our muddy sedimentary rock contains numerous crystals of clay minerals, but these clay crystals are orientated in random directions. They're all over the place, a bit like what we can see here. However, once we start putting these clay crystals under pressure, we can actually physically force these clay crystals to reorientate themselves, and this process of forcing them to reorientate themselves will actually cause the crystals to align. So in this model over here you can see we have randomly orientated clay crystals, and they're being compressed from the left and from the right, so the compressive force is orientated like so. Now what's going to happen is this is going to cause the crystals to align themselves at 90 degrees to this compressive force. So we can see here, and we can use these black arrows to show us what's going to happen is these clay crystals will force themselves, or be forced should I say, to orientate themselves north-south. So we can see these black arrows are showing us the direction of rotation of the crystals, and this process will eventually lead to the clay crystals orientating themselves parallel to one another, but at 90 degrees to the direction in which the rock was being compressed. And so this is how we take a muddy sedimentary rock that doesn't have a cleavage, and we turn it into a slate, which is a muddy metamorphic rock that does have a cleavage. The final process, the final physical process, should I say, that can occur during metamorphism is shearing. And this one is relatively common. So as you can see, we have ourselves a rock, and this rock consists of either clasts, so it's a sedimentary rock, or maybe these are quite large crystals, so it could be something like a plutonic igneous rock. And we can see that our rock is being sheared. So this side of our rock wants to go down, and this side of our rock wants to go up. And so as we've already discussed, that's going to lead to a lot of strain being concentrated right here in the middle of our block of rock. Now, if our block of rock behaves in a brittle fashion, it's just going to break. However, if our block of rock is capable of behaving in a ductile fashion, so the level of heat is high enough to allow the minerals to have slightly flexible bonds, That will allow the minerals to flow to some degree. So the shearing process will actually end up smearing out the clasts or the crystals as the rock moves. So we can see in this case, this side of our rock is going down, this side of our rock is going up, the pressure is being concentrated, the strain, should I say, is being concentrated in this region right here. And so this is forcing the minerals in this region to deform in a ductile fashion. They're being stretched out and smeared due to this shearing process. All right, thank you for watching everybody, and have a good day.